All right, so delete all this. So we're eventually going to be doing some Excel work here today. In fact, actually, I'll just open the file up again. So we left off talking about two population examples, and we're going to keep working through some proportion stuff today. We'll take a look at how we do that in Excel. We kind of have that fourth Connect homework assignment. I'll get the also the, I think it needs to be moved because I accidentally imported, so I'll move it up here right now. I also put up yesterday that fourth Excel assignment, which after today, and with that video that I posted on Friday, should be able to make a pretty good, work through a pretty good chunk of it. Really, there's only going to be a little bit left that we have to cover, which we will cover on Friday and then finish up on Monday. It's due at the end of the week next week, so I want you to try to get kind of an earlier start on it. Try to tackle those questions where we've already worked through that. Also knowing that, you know, maybe not everybody watch that video attentively, so it might be good to go back and kind of watch what I did in Excel on that video I posted Friday. I also wanted you to be able to see everything that's an intermediate score. So you've got your original exam 1 and 2 grade. You've got the number of corrections, number of problems you correctly reworked, the number of correction points, and kind of the announcement on Canvas. You know, said how I give those. It was half points back if you got it correct, so it was 2.5 points. Then even if you corrected it and got it wrong, I still gave you a fourth of the points back, so 1.25. Right? And then I added those points into your original grade, and that's kind of what this exam 2 grade with corrections is. I then use that in your exam 1 grade to identify your highest and lowest exam, currently treating those as they're going to be your best 2 exams. So your kind of 30 and 20% weighted exams. Now, obviously, you do better on the final, things would leapfrog each other, and those could change quite a bit, right? But for right now, because we don't have that 3rd exam in, I'm kind of treating these as though they'll be your best 2, right? But your best one counts for 30%. Your lowest is only going to kind of be weighted by 20. Any questions on that before I jump into material here today? Okay. All the Excels should be up to date and graded. I will post an online quiz today that'll be a little more preference based, not as much on material, so it should be pretty easy to get 10 out of 10 on that. But I'm kind of thinking about as we move towards the end of this class, we're going to be doing something called linear regression, and I, can pull in a bunch of different data sets. So kind of thinking about maybe what your interests are, right? So it should be pretty easy. You should see that pop up today, right around noon. Okay. So let's go back here. We worked through this example last class. Here we go. This is the one that we want. We're going to look at the second example. So we're looking at the difference between 2 population proportions. So we're going to do some hypothesis testing, which everything's going to be exactly the same. The only thing that's going to be different, we said, was the test statistic equation is a little bit different. Okay? So to start out with, let's just identify the null term from this problem. So it's the same problem that we built the confidence interval for. And I'll try to make the connection between our hypothesis test result and then also what we have for the confidence interval. So we had 2011, 2010, and we want to test for whether or not Hoosiers have different views about universal healthcare coverage in those 2 time periods. So we said that we're always going to set this up as the difference being the newer time period minus the older time period. Okay. Now, if I'm thinking about, are these views different from each other? I should be thinking about anytime I see this different than, or right, that's a 2-tailed test. But how do we get there? Well, if these 2 values are different from each other, there's 2 ways we can do this. The first way would be to think about, if I want to test for whether or not these are different from each other, that means that the difference could be any other value other than 0. Right? Because if they're the same, well, then when I take the difference, I'll just get 0. Anything minus itself is 0. Right? And so then I would assume the opposite is true, which is that that difference is in fact 0, that they are the same. Now, another way to think about this is the way that it's kind of, we say it in English is, I'm testing to see, okay, is that proportion in 2011 different than the proportion of people who were in favor of this in 2010? So that's kind of, if we were to write out what the problem said, this is probably more so, it will kind of line up with that. Well, if I need to write this out in terms of a difference, if I just subtract this proportion from each side, what I'm left with is this, where this is just my difference, right? So if it's kind of hard for you to think about, if I'm just saying, are they different from each other? Well, that would mean the difference isn't zero. If that is kind of a leap or doesn't line up with your thinking, you could write out what it says in English, that the proportion in 2011 is different than or not equal to the proportion in 2010, and then just rearrange it so that you have your difference and some assumed true difference value. Now here, whenever we're kind of talking about, is it different than, greater than, less than, that assumed true difference is always going to be zero, which is what I said I'll always use for the examples that I give. Right? Now I'll show you in Excel today what happens if we don't want to use zero, but this is this is kind of more of a typical example that I would give you on the exam or on homework. Okay. Any questions on that before we keep going? So what type of tailed test do I have here? Yeah, not equal to sign in the alternative hypothesis. So I've got a two-tailed test. Right? So one thing I could do is usually we find the test statistic first, but it really doesn't matter. I can find my critical values or my test statistic first. So I'm going to just find the critical values first, and then we'll kind of transition to that test statistic. So if I've got a two-tailed test, my critical values, right, I'll have a pair of critical values at each alpha. So my critical value, and I think here, the problem we'll have to see once I go back, I believe the alpha we are told is 0.01. So I'm going to be looking for the critical values that are like my threshold number of standard deviations away that I can go, or I would see, that give me a total of alpha in my tails. Well, if there's alpha total in these two tails that are of equal size, I have half of alpha in each tail, or 0.005 in each tail. So I know the area that I want in my tails, or in each tail. I'll find the z value, that threshold z value, that represents my critical value, that would give me that desired alpha over 2 in the tail. Okay. So I can use my standard normal table, find 0.005 here in the middle. That's the probability or the area that I wanted. So it looks like I'm in between these two values. So negative 2.57 and negative 2.58. I could use the higher of the two, negative 2.58. Well, negative and positive 2.58. I have a pair of critical values. Or I can use that very last row of my t-table. This gives me the standard normal values out to the third decimal. So I just go up here. I wanted 0.005 in each tail, right? So I scroll down. The z value that would give that to me, instead of being between 2.57 and 2.58, I can say that, go out to that third decimal, it's 2.576. Okay. So I just found these critical values. Thinking about my rejection regions here is going into the tails in either direction for this two-tailed test. Any questions on that before we keep moving? Okay. So the next step would be, well, I've got these critical values. What's my test statistic? Okay. So the equation that we have for this test statistic was a little bit different. The first thing that we had to do was find this P bar, right? Now, what that represented was kind of the average proportion over these two samples. Really what it actually is kind of like a weighted mean of the proportions across the two samples, all right? It's not too tough of an equation. We really just have to have our sample size and our sample proportion, which are given to us. And then when I want to find the test statistic for the difference in my sample proportions, well, I'll use that sample difference I found, subtract the assumed true difference, which I can kind of ignore this a lot of the times, because this assumed true difference is just 0. And then here we said, in order to ensure that this test statistic is a z value, because we just have an assumed true difference of 0, that doesn't tell us anything about what the assumed true values of each proportion are. They could both be 0.5, they could both be 0.2, and depending on what they are, that would change what the standard deviation of my distribution is. So using this idea or using this P bar kind of accounts for that. And then I'm still kind of using some type of a divided by n, right? Or 1 over n, multiplying it by 1 over n from each sample size. Okay. So this is just kind of our formula that will ensure that we have a z statistic, right? That our test statistic comes from that standard normal distribution. I mean, these are going to be values that are given to us. So it's just a matter of plugging things in. And then we always use that assumed true difference here of 0. Okay. So if I do that, so we had our critical values, our test statistic. Here's all the information we were given. We're just going to plug in our sample sizes of 600, 607, 0.84, and 0.82. And P bar is approximately 0.83 here. Kind of the average proportion across the two samples. We'll then plug that in, P bar in here, our sample sizes, our sample proportions, that assumed true difference of 0. So I didn't even really write that in there. Subtracting 0 doesn't change anything. And I end up with a test statistic of about 0.93 if I round to the second decimal. Okay. So, the sample difference we found was 0.02. The assumed true difference was 0. So I was 0.02 away from that assumed true difference. But how many standard deviations away is that? Well, if my standard deviation was 0.01, that'd be 2 standard deviations, right? If my standard deviation is 0.02, it's only 1 standard deviation. So essentially what we're doing is taking that sample difference, dividing it by the standard deviation, which would then tell us the number of standard deviations away our sample evidence was. So ours wasn't quite a standard deviation away, right? 0.93 standard deviations away. But once I have that test statistic, I'm just going to go back. I could use the critical value approach to make my rejection decision. So I've got that 0.93 as my test statistic. So that z statistic of 0.93. If I just plot that against my critical values, I can see it's not in my rejection region. So the visual here makes it pretty easy to see that I should be failing to reject. I'm not in the rejection region, right? But even if I didn't draw this out, remember we said that the absolute value of my critical value is less than the absolute value of my test statistic, then I should reject here, right? Well, the absolute value of my critical value is 2.576. Is that less than the absolute value of my test statistic? No, it's not. So just like the visual told me, if I just wanted to use this formula without drawing the distribution out, I should be failing to reject. Right? So this was kind of like, here was my rejection decision, but that didn't hold, so I failed to reject. Any questions over anything there before we keep moving? So really, other than the test statistic, like the steps are all the same as we've been doing. Right? So I'm going to draw this out on a separate distribution here, where I don't have my critical values up there. I'm just going to have my test statistics. So here was that z statistic of about 0.93. Now remember, we originally started out with a two-tailed test. So if I wanted to find the p-value, or the probability that I saw the sample evidence that I did, or anything further from that assumed true difference that went against the null, well, that would be everything over here, but it would have been equally as likely, excuse me, to see something on the other side of the distribution that was as many standard deviations away, but below that assumed true difference. But now for a two-tailed test, all of these values would go against the null as well. So I can find the area in one of my tails, but I have to remember, I've got a tail on the other side of equal size. So I need to take the area in that one tail and multiply it by 2 to get my total p-value for a two-tailed test. Okay. This is only for a two-tailed test where, yeah, I'm only going to see one sample difference, and that's only going to give me one test statistic. But I know that it would have been equally as likely for me to see something or sample evidence on the other side that would have also went against the null. Okay. Now I can look this area in the right tail up one of two ways. Right? The first will be, well, when I go to the table, I have to look up the area to the left. Right? or it tells me the area to the left. So if I look up this test statistic of 0.93, it'll tell me the area to the left. I'll then have to subtract that from 1 and then multiply it by 2 to get my total p-value. Right? Because this tells me the area in the right tail. To get my total p-value, you need to take the area in the right, multiply it by 2. Now, I could also remember this as a symmetric distribution. So instead of looking up for a two-tailed test, my test statistic of 0.93, I could look up negative 0.93 and just know the area that's below negative 0.93 would be the same as the area that's above positive 0.93. So then once I have that, I could just multiply that by 2 and I should get the same value. So we'll kind of see if that plays out here. So let's go first. Look up that 0.93. So 0.93, 0.8238. So 0.8238. Subtracting that from 1 gives me what? 0.1762. And then multiply that by 2, I get what? 0.3524. Right? That would be my total p-value. Now, I could have also looked up negative 0.93, in which I should find 0.176. So we'll see if that's true. So we go down here. Well, this is the 3 column, I think. Yeah, so negative 0.93, 0.1762. So the area here, 0.1762, multiply it by 2, I would get that same p-value of what? 0.3524. Okay. So either way will kind of result in you finding the same value. It's just whatever way kind of is easier for you to think about it, right? You know, if you just want to think about, yeah, I got to find the area in this to the right of my test statistic, and then I've got a tail on the other side, multiply by 2, or remember it's symmetric, so I can find the area in the left tail and simply multiply it by 2 as well. Both should give me the same value. Okay. Any questions there before I keep moving? Okay. So our rejection decision is if the p-value is less than alpha, we should reject, right? But here, for my 3 kind of conventional alphas, is my p-value going to be less than any of them? No. So I should be failing to reject. I fail to reject that assumed true difference of 0 at every single level. Okay. So to make this connection, this hypothesis test is telling me, let's see, where did we go back? Right here. Okay. So my hypothesis test was telling me, yeah, I can't reject the assumed true difference of 0. Right? I can't reject that as the true population difference at any level, which means that my confidence intervals should have all included 0 as a possible value for the true difference, which we only did 1 level. So at the 99% confidence level, remember, we said we can't really say anything interesting here because 0 is one of the values. So 0, this confidence interval tells me with 99% confidence, the true difference is somewhere in this range, and one of those values could be 0. So when I do the hypothesis test for the value of 0, and do a two-tailed test, I should be failing to reject, right? It could be one of the true differences. In fact, if I did a hypothesis test for any value in this range, I should be failing to reject every single one of them. All right, that's kind of how my confidence interval and hypothesis testings are tied up. They're both trying to figure out what values could the true difference be. It's just here with confidence intervals, we're saying here's all of the possible values at this level of confidence. If I do hypothesis testing, I can say certain values I can reject with a higher probability or a higher likelihood or confidence than others, right? So it's kind of allowing me to say slightly different things, but both of them have the goal of, can I say that this certain value is a possible, true population difference or not? Here, 0 is in my confidence interval. So when I do the hypothesis test, I should be failing to reject 0 as one of the true value, possible true values. Okay. Any questions on that before we keep moving here? Okay, so on Canvas, under the in-class data folder, I have this 2 population hypothesis test for HT blank file. So we're gonna work with that, do some proportion stuff in Excel. Okay. So I've got two different samples. One is these Southern schools, right? And I had this 1-0 variable for whether or not there were more female than male students, or at least undergraduates, at that school for every single school in my sample. I also had this Midwest worksheet, and it had the similar thing, but for schools that were located in the Midwest. And not every school, but a sample of them. Right? Universities, I should say. So first, I'm just going to work on this Midwest file and go over here, and I want to find my sample proportion of schools that have more female than male students. Well, I've got this 1-0 variable that represents that. So finding the proportion is just a unique case of the sample mean. It's finding the mean or the average of a 1-0 variable, which I have over here, right? So Control Shift, Command Shift on a Mac, select that column of data. For my sample size, I can use what function? Yeah, it's just use that count function, select my variable. It'll count the number of cells that have data in it. So I got my sample proportion of this Midwest sample, and I've got my sample size of this Midwest sample. I'll then go over to the South worksheet. I'm going to scroll over here. I can do the exact same thing. Let's actually make this a little bit larger. I'm actually going to copy this down here because I know there's something we're running into probably in a second. So I can find my sample proportion for these Southern schools for the proportion of schools that have more female than male students. So I'll select that variable. And then once again, sample size, I can use that count function. So I've now got my sample proportion and my sample size for Southern schools. I want to put the values I had from that Midwest data sheet. Now I could just look at it and type them in here, and it won't be as useful for us to use cell references in this case, but in a lot of other situations it would be. So imagine like maybe I'm doing something where I only get sample data at the beginning of every month, but I can kind of update that data set every single month. And if I had the cell references right, I would just copy paste the data in and everything would update for me, right? So what I'm going to do here is put an equal sign, right? Instead of putting the number in, I'm going to go to this, click on this Midwest sheet. Notice up here in the formula bar, it's using the reference. So just like we have cell references, there's worksheet references as well. So it's just the name of the worksheet with an exclamation point, right? So it automatically puts that in there for me. And then I just select the cell on that sheet that I want to put on the other sheet, right? So I didn't have to like type in, I just equal sign, clicked on the worksheet, clicked on the cell I wanted, hit enter. It sends me back to the original worksheet. And now it's kind of grabbing that value, right, across worksheets, okay? Now, if I copy this down, it'll keep that cell reference, same worksheet, but update, right? I copied it down one row, so it'll update it one row, which is helpful because on the original worksheet, I put the sample size right below that sample proportion. Okay? So as long as I have it structured kind of the same, it's kind of nice to just drag that down. Okay? Any questions up to this point? Okay, so if we go back to last class, and we'll go back to hypothesis testing after this, but we did confidence intervals, right? When we were looking at the difference in these sample proportions. So just to kind of remind us what that formula looked like. Sorry, taking me a little bit of time to write this out. There we go. Where this represented the standard deviation for the difference in my sample proportions. Okay. So I've got all of these values already in Excel. The only thing left I need to find is that Z value that gives me alpha over 2. Okay. So when I go to do this, right, I can think about I'm looking for this Z value that would give me alpha over 2 in each tail. Okay. So think about this is my Z value that gives me alpha over 2, and then the negative Z value gives me alpha over 2 in that lower left tail. So when I go to Excel, I now know the area that I want in my tails, right? Alpha over 2 in each. So I can use that norm.s.inv function and simply tell it, if I told it alpha over 2, it's going to give me that negative z value. And then I could just take the absolute value because I know that the positive and negative sign are already built into that confidence interval formula. I could also use just that norm.s.inv. I missed the dot somewhere here. And if I want to find the positive value, well, then the area to the left of that would just be 1 minus alpha over 2. Right? So both formats should give me that positive number of standard deviations away that I need to go. So I'm going to go back to that worksheet. And I think here I've got the difference, yeah, for Midwest and Southern schools, more female students, right, than male students. Now I said Midwest and Southern here. I'll be a lot more clear, like on the Excel homework, like the Word document kind of identifies what group 1 and group 2 are. That way you know the order. Here it's supposed to be Midwest minus the South. If that's not completely clear, like it would be in that Excel homework, it'll tell you, you know, take proportion of Midwest minus proportion of the South, right? So here, I'm going to do norm.s.inv to find these z values first. Now I'm just going to use that 1 minus alpha over 2 instead of using the absolute value function, but both ways should give me the same positive z value. So just, I know the area that I want in that lower left tail. Or sorry, I know the area I could say that I want in the lower, I know the area I want in the right tail, which means I know the area I want in that left tail as well, right? I want alpha over 2 here, 1 minus alpha over 2 over here. So that should return to me this z value. Now when I copy this down, it'll update the cell reference to using the new alpha, and I've got the number of standard deviations away I need to go to build my upper and lower bounds at each of these 3 different confidence levels. Okay. From here, it's just using Excel to be our calculator. So one thing I said to do by hand, and it often helps out a lot in Excel, is to break things down into steps. So I'm going to use Excel to just calculate this, right? The standard deviation of the difference in my sample proportions. So let me see. There we go. And I don't know what, this is supposed to be an N, right? So I'm just going to go up here. I'm going to put that in a separate cell, and then I only have like one value or one cell reference that I need to use. So we'll take the square root of my sample proportion times 1 minus that sample proportion divided by that sample size. And I'll add to that my second group's sample proportion times 1 minus that group's sample proportion divided by that group's sample size. Okay. So I'm just using Excel to be my calculator and kind of breaking this down in steps. Any questions on that? Okay. Excuse me. So we get about 0.07. One thing to kind of think about. So the standard deviation of our sample proportions. I just want to point this out. If my proportion is always between 0 and 1, right? So I'm taking a number that's less than 1, multiplying it by a number that will be less than 1. So if I do that, I can only end up with a new value that's even more less than 1, right? Like 0.1 of 0.5 is an even smaller. So I know this is going to be less than 1. If I then divide it by my sample size, anything over 1 would make this even smaller. So I know that these two values are both going to be less than 1. In fact, I know that at most 0.5 times 0.5 is 0.25. That's the highest value that numerator could be. So my standard deviation of my sample proportions should always be small. It should always be somewhere between 0 and 1. Right? No matter what my sample proportions are, it should be somewhere between 0 and 1. So sure enough, right, I get about 0.07. Right? And this is only when I'm dealing with my proportion examples. Okay. So from here, it's just a matter of getting this equation entered into Excel, having it do the math for me. Well, my lower bound is just going to be take the difference between the Midwest and the Southern proportion, subtract whatever that Z value I needed was, multiply by, well, now I just have this one value for this that represents the standard deviation for my difference in sample proportions. And that's up in that cell. And that's all I have to do. Now, if I wanted to do this all in one line, the equation that I had here, I'd have to also type out here. It just makes it a little bit more difficult, I think. You can do it that way. It just makes it more difficult. Any questions on this before we keep moving? So to get the lower bound at my different confidence levels, I want to just copy this equation down. The only thing that's going to change, I'm seeing the same sample evidence. The only thing that changes is my alpha and the corresponding Z value or number of standard deviations away I need to go. So I'm going to freeze every cell reference using F4 or Command T on a Mac that isn't that Z value. Once I freeze those, I can copy this down and I've got my 3 lower bounds pretty quickly. Okay. I'm then going to go in, I'm going to copy, hit enter to get out of the cell, and then just paste that formula in so it doesn't update any of the cell references, and I should get the exact same value. But I know that if I'm my upper bound, instead of subtracting that margin of error, I'm going to be adding that margin of error. Okay. So I just copy and pasted that cell and then changed the negative to a positive sign there where I was adding my margin of error now to get my upper bound. Okay. Any questions on this before I keep going here? Okay. Just going to hit enter, copy this down. So I've got my 3 confidence intervals here. One thing that I just mentioning, I kind of graded the Excels. Overall, pretty good. One thing that you have to, to get full credit on these Excel assignments, you need to be using these norm.s.inv functions to find your Z values. If you simply type in here 1.65, I understand that you probably did it by hand, and that's what you would find if you're using the table. The whole point of the Excel assignment is that you're using the stuff in Excel to be a little bit more precise, right? And also to make things so you could automate it. So you wouldn't have to rework this every single time. If you went back in and you re-uploaded this data for, like, instead of 2012, maybe you copy and paste in the 2020 data. Well, then all your cell references would update everything automatically, right? So I want you to be able to set these up in Excel, use the built-in norm.s.dis, norm.s.inv functions to get full credit. I need you to kind of use those built-in Excel formulas, okay? The other thing that some people try to use, and I tried to say that you weren't going to do it right, and apparently people don't listen to me, but that confidence.norm, or using the confidence formula, it is difficult to understand exactly what, if you don't have a perfect understanding, it's difficult to understand the black box, and it's very difficult for you to use it correctly. And I think there was only one person that used it correctly that tried to use it, right? So I don't show you that way for a reason, because it's a lot easier to learn what we're doing here in Excel because it matches up easier with what we're doing by hand, as opposed to that kind of black box confidence or confidence.norm formula, where things that are labeled in it aren't exactly labeled correctly for how we're using or for what we're doing. And so I think the easiest way is to kind of set it up the way I have here, excuse me, to kind of avoid not using that correctly. Okay. Maybe if we have time here next week, I might show you a little more about that confidence equation, but it's not as useful as it seems. Okay, any questions before we kind of keep moving here? So we've got our confidence interval. I'm going to see one of the cells again, or okay. So now we're going to move over here, and maybe I'm going to move some of this stuff up so that we can see what I'm doing a little bit easier. Move these zeros over here. And then I'm going to take all of this hypothesis testing difference all the way down to that 0.01. I'm going to cut that. I'll paste it right here. That way, just when I'm working, you can kind of see what I'm grabbing. You'll see, I don't have to be scrolling around as much. So let's first think about if I've got this hypothesis test and I've got it set up as the Midwest minus the South, and I've got what type of tail test here? So less than sign in my alternative hypothesis. So I have a less than sign left tail test. Okay. You should be able to know this quickly. I know maybe we don't like to speak up, but right, less than sign the alternative hypothesis, left tail test. So when I'm thinking about my critical values, if I've got a left tail test, these critical values will just be the Z values that give me 0.01, and we're going to find all three critical values here, 0.05 and 0.1. We said for a left-tailed test, my critical values should all be what? See how someone mouth it, right? But they all should be less than 0 or negative. Right? So what we're going to do in Excel is, well, we know that we want the Z value that gives us 0.01, 0.05, and 0.1 in that lower left tail. So it's just like with confidence intervals. We know the area in the tail, so we can use that norm.s.inv. Here, it's just the area in the tail for a left tail test will just be alpha. So left tail tests are kind of easy, right? Alpha is the area that we want in that lower left tail. We want to find the corresponding Z value. So that's all we have to tell it, is that alpha is the area in that left tail. So we'll go here, norm.s.inv, simply alpha, and I got my critical value. I think I had critical values because we could have a two-tailed test. We didn't. So in this case, it's just a critical value. I could then make my rejection decision using the critical value approach if I knew what my test statistic was. Right? So I've got each one of these critical values now, the rejection region being the area to the left. I now need to plot my test statistic and see, does it fall in any of those rejection regions? So what we're going to do is have Excel. We're going to use Excel to do our math for us, calculating this test statistic. Right? So leave this open up here. So the first thing we're going to do is find this intermediate step of P bar. Now, I guess if I really wanted to, I could plug P bar into here and do it all at one time, but that's a lot of parentheses and really easy to make a mistake. So here I'm just going to say, okay, take my first group's sample size times their sample proportion, add the second group's sample size times their sample proportion, then divide that by the sum of the two sample sizes. So sample size from one group plus the other. That should give me P bar, or kind of this average proportion I found across both samples. Any questions there? Okay. So I'm going to hit enter here. Now for this test statistic equation, I'm going to find the difference in the sample proportions. Right. I'm then going to subtract that assumed true difference. Now, I've got an assumed true difference of 0 here, but I'm going to eventually show you what happens if we didn't have 0. So I'm still going to select that cell reference. In practice, if your assumed true difference is 0, you don't have to, right? Subtracting 0 doesn't change anything. Now here I've got to be careful. I got to make sure I put this all in parentheses so that that identifies this is my numerator, and I want to then divide that by that square root of all of this. So the square root of P bar, which is what, up in cell S13, times 1 minus P bar, which was in S13. Kind of annoying that I can't just select it. Oops, not divide by. Multiply by 1 over each group's sample sizes, right? So I'm just using Excel to be my calculator. Instead of typing the numbers into Excel, I'm clicking on the cells. Sorry, what did I just say? Instead of typing my numbers into a calculator, I'm just clicking on the cells that have the values in them in Excel. Okay. So, but this would be exactly what, if I'm typing this into my calculator, I'd be using the same kind of thing. It's just I'd have to be typing in numbers out to the third or fourth decimal as opposed to just selecting the cell that the numbers are in. Okay. Any questions up to this point? You good? Okay. Oh, what did I do wrong? As for square root. Oh, it's not in cell S, it's in cell, sorry, T. I looked at that wrong. There we go. So negative 1.48 standard deviations away, or 1.48 standard deviations below, that assume true difference. Right? So if I'm looking at my critical values, oh, here it is. Negative 1.48, my critical values were negative 1.28, negative 1.64, and negative 2.33. So my test statistic of negative 1.48 would be here. So I'm in the rejection region at the 10% level. So I reject here, but I failed to reject at the other two. Right? Now the visual makes that pretty easy to see, but I want to have this in Excel and I can't draw out. Well, I guess I could probably like insert, do something right, put it in Excel, but it's going to be difficult to have this drawing out, right? And the drawing wouldn't automatically update if the original data or something changed. So we said our rejection decision was, is the absolute value of my critical value less than the absolute value of my test statistic or Z statistic? I should reject. So here, my critical value, right? I could do that at each single level, or I can kind of use that if statement in Excel to make my automatic decisions pretty quickly for me. So I want to say, is the absolute value of my critical value. So for a left tail test, these absolute values matter because now we're dealing with negative numbers. Right? So absolute value of my critical value, if that's less than the absolute value of my test statistic, right, then I know I should be rejecting. So if that holds, comma, if it's true, put in the word reject, comma, if that doesn't hold, or if it's false, put in the words fail to reject. And we have to use those kind of quotation marks around them so that it knows that I want to put text into that cell. Okay. So when I copy this down to make my rejection decision at every single level here, I don't want my test statistic to change. The sample evidence I found is exactly the same. I'm just using that sample evidence to test at different levels that'll have different threshold Z values or different threshold number of standard deviations away. So I want that critical value cell reference to update when I copy this down, but not my test statistic. So I'm going to go freeze that cell reference to have my test statistic in it. Now when I copy this down, just like the visual says, I should be failing to reject at the 5 and 1% level, but I can reject that null hypothesis at the 10% level. Any questions there? Okay. So if you want to see a cell again or something, let me know. We've got our critical value approach. The other way we could do this is using our p-value. Right? So with our p-value, and I actually could probably put this on the same graph, I've got my test statistic. For a left-tailed test, my p-value would then be just the probability I saw the test statistic I did, or anything below it or to the left of it, because it's a left-tailed test. So I don't have to worry about multiplying by 2. I don't have to worry about any of that. Left-tailed test, it's pretty easy. I know the test statistic. I want to find the area in that left tail. So instead of working in the inverse, where we knew the probability and wanted to find the Z value, we now have a Z value and want to find the probability. So instead of using norm.s.inv, we're going to use norm.s.dist, right? Where we tell it our Z value or our Z statistic here. And then comma 1 always gives me the area to the left. If you put in false, it's going to like give you the probability of an infinitesimally small area. It doesn't really have any use for anything we're going to do, or I'm not even sure what use it has for any, I don't know where that's useful. Also, if you want the area to the right, that doesn't mean you put a 2 in instead of a 1. So I saw a lot of people make that mistake, and I know that I mentioned it before, but we're always going to have a comma 1 there for that norm.s.dis to make it cumulative, give me the area to the left. Unfortunately, there's no way that you can use the norm.s.dis to find the area to the right. Well, I mean, you can, just not within that formula. I can find the area to the left and then subtract it from 1 to find the area to the right. But changing this value doesn't change what if it's looking to the left or the right. You can always just tell it, just make it cumulative. So think about when you use this formula, it's always only going to give you the area to the left. Okay? And instead of 1, you could put in the word true there. That's kind of, I think, a lot of versions of Excel, it tells you to make it either true or false, but it treats kind of true or 1 is exactly the same. Okay. I just think one's like it switches it on. I just always kind of thought about that way. So I get a p-value of 0.069. I could make my rejection decision using the p-value approach. So if we remember there, hopefully I get the same outcome, but we only reject if my p-value is less than alpha. So I can use the if statement again and just say, okay, look, if my p-value is less than alpha, comma, put in the word reject, comma, if it's not, put in the word fail to reject, right? I'm just taking this thing that I want to check to see if it's true. Is that p-value less than alpha? If it is, I want to reject. If it's not, I want to fail to reject. And so I'll kind of have those words put into that cell. Okay. Now, if I copy this down, like I want my different alphas, right? I want to see, can I reject these different confidence levels? But I'm always using the same p-value. My sample evidence didn't change, and so the test statistic won't change. So I'm using that same p-value. So I'll look at that p-value cell reference, and I'm going to freeze that. Right? So I'm still using the same p-value, just comparing it to different threshold alphas. Now, when I copy this down, hopefully I get the exact same decisions I did with a critical value approach. Okay. So either way is fine to make your rejection decision. Excuse me. Let me think if there's anything else I want to say there. And they should, they both lead to the same rejection decision. I think putting the p-value approach in the if statement to me is a little bit easier just because you don't have to worry about absolute values, but either way will get us to the right conclusion. Any questions over anything I did there? You want to see a cell again or? All right, so it's a little bit tricky. Not too terribly tough. All right, we just were able to reject this assumed true that the difference was greater than or equal to 0. So anything in that range, I should be able to reject as well. So I don't have to always use 0. I could say, is that difference greater than or equal to 0.1, right? So is the gap in between the Southern and Midwest schools proportions greater than 0.1, right? Or that's my assumed. Now, if I update that, everything else will update. And given the sample evidence I found, well, if I could reject it was greater than or equal to 0, I definitely can reject it greater than or equal to 0.1, right? But I can use different values. So maybe I actually even want to do like negative 0.05, right? So, and I can't reject that difference is closer than 0.05. Right? So I won't expect that of you guys on the Excel assignment or anything like that. But just in practice, like outside this course, you could do that, right? So maybe I want to say something like, is the proportion of people who are in favor of a certain policy different between Democrats and Republicans? And not only do I want to know, is it different, is that difference greater than 0.2, right? Or greater than a 20 percentage point difference. So I could do things like that. But for us, we're going to keep it kind of simplistic and keep things at 0, okay? Any other questions for me before I let you guys get out of here? Okay, so remember that online quiz will show up in just about an hour. What we do before we start on Friday. Should be pretty easy to get all 10 out of 10 points on it. Other than that, I'll see you guys Friday.